So I'm going to talk a little bit about things I've been doing the last few months, 6 months or almost. So it's called Tailflow, and it's about Openflow. So I'm working for Tailflow Systems, a company founded in 2005 by some old colleagues of mine from CS Lab, former Bluetail guys. They are making two products called ConfD and NCS, and I will mention them briefly because they are part of the Tailflow solution. So, number of customers, of course, big customers, small customers worldwide, as you can see here. And it's about network management. So, let's see. So, hopefully you will learn something. I assume that you don't know anything about these things, otherwise you already know about it. So, hopefully you will know after this talk what SDN means, or what it stands for, at least what I think it is. And Openflow, what's that? We're going to talk about that too. And you're going to learn a bit about modern network management, the Tailflow way, the way to go, not the traditional boring kind of network management. So, and finally, hopefully we will be able to see a little demo, perhaps. Unfortunately, I sort of broke the whole system the other day when I restructured the whole system because we have a release within 2 weeks. So I thought I should redo everything the proper way. So I broke lots of stuff, but some part might work if we are lucky. So let's see. So network management, traditionally, that means lots of tedious work. I mean, imagine you're working for an operator, you have a customer who wants another leg in their VPN setup, for example. That might mean that you have to change some routes in a firewall, perhaps, change some configuration in a router somewhere, maybe some other kind of network device in your network. And if you do something wrong during that period of changes, you have to retrace your steps back and try to figure out what happened. And if you have lots of customers, huge networks, this quickly becomes a huge mess. So what you try to do is to automate stuff, writing scripts, tools, things that can automate lots of the things that you don't want to do manually. But after a while, tools change, and the tools are not as good as they should be, perhaps. After a while, you don't really know what do I have out there in my network. What is the current configuration, for example? You don't know. How does my network look like, really? You don't know, really. And it all boils down to money, of course. So that this whole process is extremely costly for operators. And so this is sort of the traditional view that Tailflow, of course, has solutions for. So an acronym that has been sort of becoming really hot the last sort of year, called SoftwareDefined Networking. SDN for short. So, I mean, if you have a large, complicated system, you often try to understand it. You have to make up some kind of abstractions. You might divide your system into a couple of large components, which sort of logic is connected in some way. And if you start to zoom in on one component, a smaller subcomponent appears suddenly with their own interfaces within that large component, etc. So you build sort of abstraction levels to be able to cope with this complexity. So the question is whether you can do that in a network management situation, where you have this large, huge network of thousands of devices of various sorts, heterogeneous devices from various kinds of vendors. Because if you could build some kind of abstraction, then you could start applying perhaps software engineering practices and techniques. And the goal is to, again, money. If you can reduce the time to deployment, if you can reduce the amount of errors when you introduces new things or changes things in your network, you also reduces cost. So this sounds fantastic, but can it be done? Yes, it can, of course. So here's a very complicated picture that I stole from some marketing materials. So I'm going to talk you through it a little bit here. So down here we have firewalls, routers, network devices out there in the network. A possibly very heterogeneous network. If you can describe one of those devices in some way with a model, an abstract model of that network device, if you can describe it with an abstract model, then suddenly you can sort of represent it also as with some sort of data structure in your system. And if you have a data structure, then you can start to manipulate it and do stuff with it. And this is how those products, NCS and ConfD, they are taking advantage of the possibility of describing devices with an abstract model. And the language used is a modeling language called Yang, which is sort of closely connected to netconf, even though it can be used by its own, I guess. So netconf is an XML-based protocol, which makes it possible for you to operate and configure devices over the network. So this model, the abstract model, can be transformed into XML and can be passed along using this netconf protocol to configure and operate this device. And the difference between, one of the main difference between netconf and SNMP is that with netconf you can differ between operational data and configurable data. In SNMP you can't do that really. So this means that you can both get status operational data out of the box and you can configure it in a consistent way using netconf. So this raises the abstraction level. Suddenly you can start to discuss and you can analyze what is the current configuration of my whole network here, because you have it here as data structures. You can start to manipulate them, analyze stuff, writing tools for them, etc. So this abstraction level can be taken one level further. So using those device models, we can introduce configuration changes in an atomic way over several devices in a transactional manner, which is kind of extremely important, because if something goes wrong when you have done the half of the sort of devices you want to change or configure in some way, you can undo the transaction and undo everything that you have already done, and you can get back to the previous state which was hopefully consistent. So device models makes it possible for us to operate those network devices in a consistent way. The next abstraction level that we have introduced is called service models. Again, we're using Yang to model services. So a service could be, for example, creating a new VPN leg for a customer. And then we could, by using some kind of logic, break that services down into the proper device, manipulating stuff that we need to do. So at the end, it comes out as configuration changes down here in the network. So this makes it possible to actually have this kind of abstraction level to manage your network in a consistent way using those mechanisms, the models and both device models and service models. So let's see. So yeah, right. So to me, this is kind of software-defined networking, which makes it possible to do this abstraction and to actually programming services in the network that you are managing. Now we're going to talk a bit about Openflow, and then we're going to relate that to SDN to see how it fits into SDN. So Openflow, to me, if you buy a firewall or a router or something, you buy a box, pizza box perhaps, you have some hardware, and controlling the hardware you have some kind of software, which is the logic that controls that firewall or router, whatever it is. Now with Openflow, they have made it possible to move that software out of the box. So you can write your own software, and they define this protocol that talks to the hardware. And that's what Openflow is about. It describes this protocol talking to this hardware. So this makes it possible for anyone to actually write their own control logic of the network device. So this came out of some university work. I guess they like to be able to fiddle around with things, but it has actually taken on quite of interest among the industry too. So Openflow has been kind of a hot topic the last few years. So what happens is that this software here is, in Openflow terms, is called a controller, Openflow controller. This hardware here is really just a table trying to match the headers of the incoming packets to see if any packet matches what you have specified in your table. And if it does, it's going to produce a set of actions which is coupled to that table entry. And in case nothing matches in the table, we have to ask the controller, what are we going to do with this packet? And the controller can instruct the hardware to do something, either send it out to a certain port, or rewrite a part of the header, or just drop it on the floor, perhaps. So here is just an example of things that exist in this table. So this is a table entry where you can match incoming packets on, for example, what switch port it came in through, the ingress port, Ethernet source address, IP source addresses, and lots of other stuff in the headers of the packets. And connected to this table entry, you also have this set of actions. And the actions you can do is sort of send this packet out on a certain port through the switch. You can rewrite any of those headers into something else. So you can implement, for example, a network address translation firewall, for example. Or you can just drop it so it won't get through the switch at all. So basically, that's it. That's what Openflow is about. So it's kind of not that complicated.
But if there's some kind of language to describe those rules?
Yeah, flow rules. Yeah, they are described. It's not a language. It's just a protocol spec. So you send sort of messages to the hardware, and you can add, install those rules, and modify rules, and remove rules, etc. They can also, of course, get lots of operational data, like counters and things like that. So, yes.
Is the actual packet forwarded over to the software?
Yeah, it can be forwarded, and it can also stay in the hardware, and then you will get a reference to it. So the controller can say that, hey, you're going to send this packet with this reference out again, or send this packet, and also perform the actions at the same time that I want you to do. And at the same time, install a rule so that any packets in the future that matches the same thing won't enter the controller. So, but anyway, when you have this kind of Openflow capable switch, I mean, it still needs to be managed. It's still going to live in this network that operators are managing. So you still have to have some kind of management interface. I mean, for normal box here, you have a command line interface, CLI, or you have SNMP, you have netconf, etc. You're still going to need that for an Openflow application of some sort. You can, of course, choose whether you only have it on this level, or perhaps if you want also be able to manipulate the hardware straight from your management application. So SDN versus Openflow. to me, Openflow is just a component of SDN, because Openflow application is just like any other network device that you need to manage, that needs to coexist with all the other network devices, firewall, routers, etc. And software-defined networking, even though it's fun to program, so the important thing to remember is that it's about programming networking services. You want to be able to introduce networking services in an easy way, in a cost-beneficial way, and hopefully these kind of approaches can solve that. So, how do I write an Openflow application? I started to look into Openflow, reading the specs and reading what other people had done, and most of the examples, or almost all examples, stopped at some very basic, simple learning switch, and then you were sort of on your own. And I mean, when you start looking into it, you quickly realize that Openflow rules are extremely low level. I mean, if you want to write any kind of application on top of an Openflow hardware, you need to do lots of stuff. And how do you structure that? And also, since I was working for TLF, management is extremely important for us. How do you manage that kind of application? So I started to writing programmatical patch panels. I wrote sort of load balancers, etc. in Erlang, controlling. Mostly I was using OpenVSwitch, which is a software virtual switch which you can install on your Linux system. You can replace the standard Linux bridge with the OVS, as it's called, because OpenVSwitch is actually an Openflow capable switch. So you can create each bridge you create on OVS is an Openflow switch that you can control from your software. So it's a very, very easy way to get into Openflow and start playing around with it. So I wrote lots of those small, simple sort of examples. And after a while, I started to think, I was trying to figure out how to structure the software in a good way. And I started to remember work which were done sort of for some 20 years ago when it comes to communication protocols. Because at that time, it was kind of a hot research topic, something called microprotocols. And, perhaps I should go right here. So, microprotocols, if you look into, for example, TCP, you can extract various pieces of TCP and look at them as sort of small microprotocols. For example, sliding window could be seen as a microprotocol. Fragmentation, defragmentation, and other stuff, and put them together in a graph, and you have your sort of protocol. And that was a research topic, and both Cornell and other universities, University of Arizona, they did lots of work. So there were a system called Horus at Cornell, I think, which implemented frameworks for you with a sort of library of lots of microprotocols that you could put together to form new kind of protocol stacks. And there's actually a book written about it from some guys at University of Arizona. They call it Computer Networks. Peterson, Davey, or something, are the authors, where they describe this X-kernel. So I played around with that for 20 years ago, writing stuff in Erlang. So I thought perhaps that could be something that I could use to structure it, to write small kind of pieces of logic that I can combine to actually build my software application controlling that hardware. So, if you look at the Openflow controller, from the Openflow controller's point of view, the switches produces a number of events, not that many events, a few events, where the most important is when a packet misses the table, it has to go to the controller, so you get a packet into the controller. Then you want to take some actions, you want to do something with that packet, you have to decide what to do with it. So that's an event that's generated from the hardware coming into the controller. Other kinds of events are, for example, when a switch connects the first time to the controller, a data path join in this case. Or if a flow is removed from a table entry is removed from the hardware, then you might want to know about that. So another entry, a flow removed entry, might enter the controller. Because each flow has timeouts connected to them, so they both have idle timeouts and hard timeouts, so they can automatically be removed by the hardware. So for each of those events entering the controller, you want to apply some kind of logic, doing something, take some action on that event coming into the controller. So I came up with this idea using something I call Flowlets. So Flowlets, the idea was to, well, instead of a micro protocol, I call it Flowlets because a Flowlet consists both of some Erlang code and also some configuration specified or defined in a YANG model. By combining those Flowlets in a stack, you create the actual software that controls the Openflow switch. So in this case, for example, we have a learning switch which also introduces some kind of a layer 2, virtual layer 2 mechanism, so that you can, for example, you can have one company run like VLAN, but you write your own sort of layer 2 abstraction here. So the idea is that a packet enters from the top on the switch stack. So a packet comes into the controller, enters the first Flowlet, in this case called the Mac learner. The only thing the Mac learner does is to look at the packet and see what switch port did it enter through and what kind of MAC addresses were in the packet, both source addresses and destination addresses. And it stores that information. So if packet enters through port 1 with a certain source address, I store that into a database in the system. And that's everything it does. And then it just, well, finish, and the packet goes to the next Flowlet in the stack. In this case, the ARP replier. The ARP replier, it can answers to ARP requests. So you can, by configurations, saying that, all right, for this kind of IP address, I want it to work as an ARP proxy. So then you should answer with this Ethernet address, preferably the Ethernet address of the port, perhaps. And if it's not an ARP request, then it does nothing. So the packet just goes through the chain to the L2 filter in this case. And the L2 filter Flowlet in this case, it adds a number of rules. So it's sort of a little rule engine adding where you can specify some rules. For example, you can specify that a certain amount of Ethernet addresses belongs to a certain virtual net. So they should be able to talk to each other. So if you're trying to send to someone within that group, that's okay. Then let the packet through. If not, drop it on the floor, and it's not allowed to go on any further. So you introduce your own virtualization on a layer 2 level. If it goes through the layer 2 filter Flowlet, you enter up with the ARP Flowlet in this case. And what it does is simply to ARP request entering the switch, and we don't know what to do with it, so flood it out on all the ports except the ingress port on the switch. So that's the normal way ARP requests are spreading through the network. If it's not an ARP request, go to the last one, and the only thing it does is to set up a path through the switch, because down here we have to know both where the source Ethernet address lives on what port, we have seen it, and also the destination address. Because when we get an ARP request the first time, we send that out through all the ports. So a reply will enter at some point in time through another port, and we will store that through the Mac learner. So we will have that information in the Mac database. So when we enter the last Flowlet, we know where the source and destination address are from the Mac database. So we send down a flow rule to the switch and and make a connection from the ingress port to the egress port through the switch. So this is a sort of learning switch. If you remove this thing, it's just a very basic learning switch. So I implemented that learning switch and got it to work. I also implemented a simulated sort of huge network of racks with the computers in, connected with top of rack switches, with aggregating switches, with a knotted firewall that I wrote, and they all were simulated with OpenVSwitches, and they were all controlled by this Tailflow controller that I had written, and it all worked out very well. So I continued the work using this kind of architecture. So the Flowlet, as I said, consists of an Erlang module and a corresponding Yang module defining what possible configuration that Flowlet can act upon. So the configuration is described by Yang, and the Erlang modules. The Erlang module can control sort of what's going to happen with the execution through the Flowlet stack by what it returns. So when, for example, when a packet in enters the controller, the packet in callback will be called from the first Flowlet in the stack. And depending on what that Flowlet returns, something's going to happen. So you have three choices in this case. You can say break, which means that don't process this packet through the stack anymore, I'm done. Or you could say continue, and the packet will traverse through to the next Flowlet in the stack. Or I could jump to another stack. So I can have multiple stacks of Flowlets, similar to sort of EP tables, where you can have several chains of stuff. Each Flowlet they are sort of stateless in the sense that they have a state, but the state is managed by the controller, the Tailflow controller. So when you start a system, load your configuration, each Flowlet will be called, their init callback function will be called, so that they can set up some kind of local state, which is returned, and then the Tailflow controller maintains the local state and threads it through all the calls through the stack. There's also an event state that can actually be threaded through the stack, which is only living during the event, so to say. So all those Flowlets configuration and all the Flowlet stacks, they form together something called the switch logic in the Tailflow terminology, and that simply defines the actual software controlling a particular switch. So the Tailflow controller can handle lots of switches, and each switch will get some software applied on all the events depending on how you have set up the switch logic for that switch. Or you can also do you can also set it up so that some default switch logic is applied to all switches. If you have hundreds of learning switches, you want to run the same software on all of those. Yes?
Do you mean that you actually take network packets that come up to the software down through Erlang and take a decision to the Erlang?
Yep.
But on the software side, not on the hardware side?
No, software side.
Is that a problem, or will you do it, or is it just for proof of concept?
No, that's how it works. So, I mean, hopefully you install a flow rule, so the next kind of similar packet won't end up in a controller, and hopefully you won't have that much traffic, because then you will be stuffed. I mean, the controller can't keep up. Yeah. So I mean, you can write applications work like that, which are reactive, but you can also think you can have a proactive case where you know exactly how you sort of traffic engineered your network beforehand, and then push down all the routes that are going to be valid, and then you're fine. Then in that case you won't expect to get any packets up into the controller. So I'm going to mention that later on, but I mean, Openflow won't replace, off-the-shelf firewalls and routers and stuff just because of this. I mean, it makes no sense to get packets up into the controller like this. But for certain problems, as we're going to see, it fits very well. You can do stuff which is hard to do with traditional techniques that you have had before Openflow. So this is how the Tailflow system looks like. So it's a controller here written in Erlang, and it's also tightly coupled to the Conf-D product, because the Conf-D product knows about Yang and auto-renders from the models of the Flowlets and other kind of Yang models. It auto-renders a northbound API with netconf as an MP, CLIs and stuff, so that it can be managed as any other kind of network device, or better than any other kind of network device. So all this kind of configuration here is applied depending on the events coming in. So the right kind of software is going to be run depending on where it comes from. So you can have, for example, in this case, we have switches, apparently A1, A2, who runs the same kind of switch logic, same kind of software. So they are always going to be using this kind of setup, where another box called B1 is using another kind of configuration. So the idea is that we're gonna release this as a part of the product portfolio of Tailf pretty soon now. And the idea is that customers are gonna be able to write the Flowlets themselves, and the models are gonna be able to load them into the system. We will of course write lots of Flowlets that can be used sort of in a sort of a library fashion. But the idea is that anyone should be able to write those kind of Flowlets to implement whatever kind of functionality they want to have in their network.
It's hard, like, it used to be very and self-handling. The number of events coming from the hardware over to the controller or TCP must be quite limited.
Well.
So if in a normal telecom system have a very huge control system.
Yeah.
Must be certain type of other things for it.
Well, the actual hardware manufacturers has been sort of been lagging behind sort of the specifications. The specification is somewhere here, and the hardware manufacturer is trying to keep up with some old sort of versions of the specifications. But there are a couple of manufacturers producing Openflow switches, and there are a couple of hybrid switches which are sort of, they have added overflow capability, but they're still sort of older kind of switches, and I'm not sure how well they really work and how well they will work under heavy load, etc. I mean, as I said, it's not going to scale if you have a very high traffic volume and you want to process that through Openflow. That won't work. But for certain problems, as we will see, it fits very well. So this is the realistic scenario. So I was thinking about this a lot the first months. I was thinking, this is fun to do, but I mean, it's not going to be used for any serious stuff. And then suddenly the customers approach us with problems they had that we thought, hey, this fits Openflow perfectly. So the idea is that if you have a number of devices, firewalls, VLAN accelerators, deep packets inspectors, intrusion detection, whatever, and you have sort of like so-called bump in the wire devices, so that you put them wire in one end and then the wire goes out in the other end, and then you send the layer 2 traffic through and the device does things for you. Each of those devices implemented some kind of service, a firewall service or a VLAN accelerator thingy. And you want to be able to, for an operator, so that he easily can set up those kind of services and tailor-made those kind of services according to what the customer needs or wants. And it turns out that apparently this is kind of hard and quickly becomes kind of messy to do in a traditional network. There are ways like policy routing, etc., but apparently it's extremely hard to manage it. So, but with Openflow, that's very easy. It's very easy to, because it's almost like you have a programmable patch panel, and you can easily switch on and program that hardware, how flow should go through that kind of chain of devices that you have plugged into your switch. So here is a sort of the concept of service chaining. So we have this Openflow switch, and into it we have some kind of network devices connected, firewalls, deep packet inspectors, etc. The Tailflow controller controls the Openflow switch. We have written a certain service chaining Flowlet for that. We have all those kind of nice device models, both for the Flowlet here and for all those kind of devices. We have a service model for service chaining that we have defined. So a customer here might want, I only want to make use of the firewall. All right, very easy. Depending on what kind of IP range he comes from, we're going to control Openflow switch, set it up so that he only will enter through the firewall and then further on. Another customer might want other kind of devices or in a chain that should first go through the deep packet inspector, then the firewall, or etc. So then we very easily can program the Openflow switch to do that. So this use case is a valid use case. We have customers who are extremely interested in doing this, and it fits very well into Openflow. So we actually wrote a demo that was shown for a fair in Las Vegas for a few months ago. I thought I would be able to show it to you, and perhaps we can see a little bit of it, because I broke it kind of heavily the other day. But basically we are using OpenVSwitch again, and we're controlling it from Tailflow. We have written sort of traffic shapers and firewalls, very small ones, just to as a proof of concept. All of this up here is running in a virtual machine that we have set up using Vagrant to make it very easy to script it and set it up for people. And from outside of that virtual machine, we have just an ordinary browser. So it can go to this VLC server, and the traffic will go through the switch and go through the change depending on how we have configured it, and we can change sort of the traffic, limited traffic speed through the shaper, etc. And well, and it's controlled by NCS, of course. So let's see here now, demo time. Right. So the whole demo was written by me, Klakke, Luke Gorey, and Niklas Bystedt. Let's see if we can find it somewhere. Ooh. So, well, you have to trust me on this, but let's see. Do you see anything? No, I don't see anything. So what we can see here is this is sending video through this switch. So we can start by looking at it a little bit, and then we can see if we can change the speed here. Wow, we have even sound. You hear it? Yes. Fantastic. Guess if I'm bored about this music on this video. So let's see if it runs there, and then if we can go to, let's see. So now I'm inside this virtual machine. Do you see it down here? I'm gonna go in, enter the GUI is broken by me, unfortunately. We had a very nice GUI, but I can't show you that because it's broken at the moment. So let's see. So this is the CLI. We are inside the NCS CLI now. Lots of commands you can do here, similar to any other kind of network device. We enter configure mode. We can have a look at the services. Let's see here, right. So here's configuration data, a chain which we have called asset, that's use defined. We define sort of where the key for this chain is the source subnet, the source VLAN, and the desk subnet. That defines what chain we're going to use. So those are the keys. And what's going to happen then is that we have two devices. So it's going to go around first through the shaper and then through the firewall. And we also know what is the ingress port of the traffic in the switch. It's port number 6. And also the egress port is port number 5. And elsewhere we have information about what ports are the devices sitting on. So let's see if we can see that here. I can't see it here. Is it somewhere else? Ah. At the top you can see the firewalls apparently there. It's a bump in a wire thingy device, so the import is 3, output 4. The shaper import 1, output 2. And the controller now, the flow service chaining Flowlet is setting up or has already set up a flow through that switch to chain the traffic through those shaper and firewalls, etc. So if we can try and see if we can change the speed. Let's see here, do I have it in history here? So set services chain, and then we'll go down into what switch logic, and then chain, shaper configuration, speed. Let's set it to 1000. Commit. Right. So now it's set to 1000. Let's go back here to the video. Where is it? There it is. Now it's cached a little bit in the browser. Let's go forward and see what happens. Ah. So hopefully it should start to lag. Do we see any lag here? Not much. Let's see if we can reload it and see what happens.
It doesn't seem to accept like
Yeah. Worked yesterday. Crap. Should we try and set it even lower? This demo is gonna be a fiasco. All right. Start lag, damn it. Amazing. Let's see if we can kill that window, and then if we... Sorry? Yeah, it's probably cached. So. Let's see. I thought I had... Yeah, I thought I had set it so that it shouldn't cache anything. No, I mean as I said, it worked yesterday. I promise. 1 minute. Oh, let's see. Can I clear any cache here? Sorry? Incognito window. Control Shift. Incognito. I want to kill the other one. I'm gonna get 2 videos. Crap. Nothing works. Sorry about that. Anyway, you get the ID. Wow. All right, so I'm sorry we won't have time for Q&A, but approach afterwards and bombard him with questions. Sure. So we're going to have a little break while we set up for the next speaker, and then we'll convene in 5 minutes.